Picture this. You're standing outside just before dawn, the sky still painted in shades of deep blue and gentle grey, when you catch sight of something extraordinary. There, hanging low on the eastern horizon like a tiny beacon, is a bright point of light that seems almost to dance in the morning twilight. It's brighter than most stars, yet somehow different, steadier, more purposeful in its glow. You watch for a moment, perhaps wondering if it's a distant aircraft or satellite, when suddenly you realize you're looking at something far more remarkable. You're seeing Mercury, the solar system's most elusive messenger, making one of its brief appearances in our earthly sky. Tonight, we're journeying inward to the very heart of our solar system, to a world that plays an eternal game of hide-and-seek with earthbound observers. A world so close to our Sun that it races around its orbit in just 88 days. Yet so challenging to observe that even seasoned astronomers consider a clear glimpse of Mercury to be something special. This is a planet of impossible extremes, where the surface can melt lead during the day yet harbour ancient ice in permanent shadows, where a single day lasts longer than 2 of its years, and where the sun appears to rise, set, and rise again in the same mercurial dawn. Hello and welcome to the Sleepy Astronomer. If you're settling in for the first time, welcome aboard our gentle drift through the cosmos. And if you've travelled with me before to explore distant worlds and quiet wonders, it's wonderful to have you back among the stars. Whether you're tucked up in bed listening to the night sounds outside your window, curled up in a favourite chair with a warm drink cooling beside you, or perhaps lying back where you can glimpse that same twilight sky where Mercury occasionally shows itself, I'm so grateful you're here for this journey. Our exploration begins where all good astronomy stories do, with ancient eyes turned skyward and the patient observations of people who noticed that this particular wandering star behaved unlike all the others. For thousands of years, Mercury has been the swift messenger of the heavens, appearing briefly at dawn or dusk, before vanishing again into the sun's glare. The ancient Greeks actually thought they were seeing 2 different objects, Hermes in the morning sky and Apollo in the evening, until careful observation revealed the truth of Mercury's singular identity. Tonight, we'll follow Mercury through its swift dance around the Sun, discovering how this smallest of planets became the solar system's ultimate survivor. We'll explore a world where temperatures swing from blazing hot to frozen cold within just a few hundred kilometers, where the landscape bears the ancient scars of cosmic bombardment, and where recent discoveries have revealed water ice hiding in craters that never see sunlight. From its role in confirming Einstein's theory of relativity to the engineering marvels required just to visit this challenging world, Mercury has stories to tell that reach from the earliest days of astronomy to the cutting edge of space exploration. There's something deeply poetic about Mercury's relationship with our Sun. While we on Earth enjoy the luxury of a temperate distance from our star, Mercury lives in the intimate embrace of solar fire. It's a world that knows the Sun not as a distant light in the sky, but as an overwhelming presence that dominates every aspect of its existence. The Sun looms 11 times larger in Mercury's sky than it does in ours, a brilliant disk so intense that standing on Mercury's surface would be like living inside the heart of noon, forever and always. Yet for all its harsh beauty, Mercury remains curiously gentle in our earthly sky. When it does appear, those precious few weeks several times a year when its orbit carries it far enough from the Sun to be visible, it shows itself as nothing more than a quiet point of light, modest and unassuming. There's an irony there that would have delighted the ancient astronomers. The planet closest to the source of all light and heat appears to us as one of the faintest wanderers, visible only in the soft moments when day surrenders to night or night slowly gives way to dawn. From the romance of its morning and evening appearances to the extreme physics of its sun-baked surface, Mercury invites us to contemplate the beautiful diversity of worlds that exist in our solar system. It reminds us that planets can be far stranger and more wonderful than our earthbound experience might suggest. Some worlds are gardens, others are furnaces. Some spin leisurely through their days, others are locked in gravitational dances so complex they defy easy explanation. Mercury is all of these things and more, a world that challenges our assumptions about what it means to be a planet. So settle in, get comfortable, and let's begin our gentle journey inward, past the familiar territory of Mars and Venus, beyond the asteroid belt that marks the boundary between the inner and outer solar system, all the way to the Sun's doorstep, where Mercury has been faithfully keeping its swift orbit for over 4 billion years. Out there, in the blazing brightness where sunlight is not a gentle kiss but a cosmic shout, Mercury waits, patient despite its speed, ancient despite its youth, ready to share the secrets it has learned from living so close to the fire that lights our days. Have you ever tried to spot Mercury in the twilight sky? If you have, you'll know it's a bit like trying to catch a glimpse of a shy friend who keeps ducking behind corners at a party. Just when you think you found it, hanging there like a bright jewel against the deepening blue, clouds roll in, or the horizon swallows it up. Or perhaps you simply lose track of exactly which point of light you are following. It's there, then it's not, then maybe it's there again. Though you can't quite be sure. The frustration is real and immediate. You might find yourself squinting through the atmospheric haze that hugs the horizon, wondering if that slightly brighter spot is Mercury or just a distant airplane. Your eyes water from staring too intently at the twilight glow. You shift your position, trying to block out a nearby street light, and suddenly you're not sure if you're looking in the right direction anymore. Mercury has this way of making even experienced skywatchers feel like beginners again, humble and slightly bewildered by the challenge of simply seeing it clearly. This is exactly the experience that has been repeated countless times throughout human history, in countless places around the world. The difficulty is genuine and universal. Mercury truly is the most challenging planet to observe with the naked eye. Even when you know exactly where to look and exactly when to look, atmospheric turbulence near the horizon can make it shimmer and dance, appearing almost to wink at you. Some nights it's brilliant and unmistakable. Other nights it's so dim you wonder if you're seeing it at all, or just imagining a star where you expect one to be. This celestial game of hide and seek has been going on for thousands of years, and it's created one of astronomy's most charming cases of mistaken identity. Picture an ancient Greek astronomer, perhaps standing on a hillside outside Athens, as the first hint of dawn touches the eastern sky. He notices a brilliant star rising just ahead of the sun, bright enough to be visible even as daylight begins to wash out the other stars. He watches it for several days, noting its position, its brightness, the way it seems to dance slightly in the morning air. Then one day, it simply vanishes, not gradually, but as if someone had blown out a cosmic candle. A few weeks pass. Our astronomer, dutiful in his observations, continues his evening watch as well. The western sky after sunset has its own character, softer than the sharp clarity of dawn, painted in warmer colours that gradually deepen from gold to amber to deep purple. And there, just as the sun disappears below the horizon and the first stars begin to show themselves, he spots another bright star. This one behaves differently from the morning star in subtle but unmistakable ways. Where the morning star seemed to race ahead of the sun, urgent and fleet, this evening star appears more stately, more patient. It lingers in the twilight, hanging on as night deepens, casting a steady light that seems almost companionable. You could imagine sitting quietly with this star, watching it hold its vigil as the sky darkens around it, until finally it too follows the sun below the horizon and leaves the night to the more distant stars. To his eyes, trained though they are by months of careful observation, these appear to be two completely different celestial objects. They have different personalities, different behaviors, different relationships with the sun and the horizon. The morning herald arrives with urgency and departure. The evening sentinel offers presence and patience. It's like watching two different actors play similar but distinct roles in the ongoing drama of the sky. And so the ancient Greeks did what any reasonable people would do when confronted with two mysterious celestial messengers. They gave them names and stories. The morning appearance became Hermes, the swift messenger of the gods, fleet of foot and quick of wit, who could travel between the realms of mortals and immortals. The evening appearance they called Apollo, the god of light and prophecy, bringing illumination to the darkening world. It's a beautiful mythology, really. Two divine brothers taking shifts to watch over humanity, one ushering in the day, the other standing guard as night falls. But here's where the story gets deliciously complicated. Some particularly dedicated sky watcher, perhaps a priest responsible for timing religious ceremonies, or maybe just someone who loved the quiet ritual of dawn and dusk observations, began to notice something peculiar about the timing. The morning star would appear for a few weeks, growing brighter each day until it reached maximum brilliance, then gradually fade back into the sun's glare. After it vanished completely, there would be a gap of several days or weeks. Then, as if by magic, the evening star would make its debut in the western sky, following its own cycle of brightening and fading. The pattern was too regular, too precise to be coincidence. Someone, and we'll never know who, first realized that Hermes and Apollo were actually the same celestial being, playing an impossibly swift game of cosmic quick change. The morning star wasn't disappearing forever. It was racing around to the other side of the sun so quickly that it could reappear as the evening star before anyone quite realized what had happened. Imagine the moment of that discovery. Picture our ancient astronomer suddenly understanding that they hadn't been watching two separate divine messengers, but one incredibly swift traveler who could dash from one side of the sun to the other, faster than human eyes could follow. It must have been like watching a magic trick and suddenly seeing how it's done. That mixture of disappointment at losing the mystery and excitement at gaining a deeper understanding of how the cosmos actually works. This realization required something that we might take for granted today, the willingness to trust careful observation over obvious appearance, and the intellectual courage to question what seemed like common sense. The eye sees two different stars. The mind, working with patience and precision, discovers one planet moving in a complex orbital dance. It's the kind of breakthrough that requires you to hold two contradictory ideas simultaneously, the evidence of your senses and the pattern revealed by careful record-keeping, until the deeper truth emerges. Think about what this meant in practical terms for ancient astronomers. They had to develop systems for recording observations over months and years, creating the world's first astronomical databases on clay tablets, papyrus scrolls, or carved stone. They had to train themselves to see subtle differences in brightness, position, and timing that most people would never notice. They had to resist the very human tendency to see what they expected to see instead training themselves to see what was actually there. Most importantly, they had to develop what we might call scientific patience, the willingness to watch and wait and record, even when the patterns weren't immediately clear. The discovery that Mercury was one object, not two, probably took generations of observers, each adding their measurements to a growing body of knowledge, until someone finally had enough data to see the underlying pattern. The ancient Egyptians seem to have made this same discovery independently, and they wove it into their religious practices in particularly elegant ways. Egyptian priests needed to time their ceremonies with celestial precision. Their entire religious calendar was synchronized with the movements of stars and planets. They called Mercury's morning appearance Sobeku and its evening appearance Set. But unlike the Greeks, they understood from early on that these were two faces of the same celestial deity. There's something almost modern about the Egyptian approach. They treated Mercury not as two separate gods, but as one god with the power to transform, appearing in different aspects at different times, but maintaining a fundamental unity. If you've ever watched Mercury make one of its rare daytime appearances, visible as a tiny disk through a telescope, while the sun is still above the horizon, you can appreciate why ancient peoples found this planet so mysteriously compelling. It's the only planet that can truly claim to be both a child of darkness and a companion of daylight. The Babylonians, meanwhile, were developing what might be called the first truly scientific approach to Mercury observation. Working from their ziggurats under the famously clear skies of Mesopotamia, Babylonian astronomer priests tracked Mercury's movements with a precision that would make modern astronomers nod in approval. They called it Nabu, after their god of writing and wisdom, a fitting name for a celestial object whose behavior they recorded so meticulously on clay tablets that modern scientists still consult these ancient observations to refine their understanding of Mercury's orbit. Picture these ancient astronomers working night after night from their elevated platforms, the Mesopotamian sky spread out above them like a vast scroll waiting to be read. They had no electric lights to interfere with their observations, no atmospheric pollution to dim the stars. The sky they watched was a crystal-clear window into the cosmos, and they treated their observations with the reverence of scribes, copying sacred texts. Each position of Mercury was noted, each phase of its cycle recorded, each variation in brightness carefully documented. The clay tablets they created weren't just casual notes. They were precise astronomical records that tracked Mercury's behavior across decades and centuries. When modern astronomers study these tablets, they're amazed at their accuracy. The Babylonians could predict Mercury's appearances months in advance, calculate when it would reach maximum brightness, and even account for the subtle variations in its cycle caused by Earth's elliptical orbit around the Sun. Think about that for a moment. Observations made by people working with nothing but their eyes, basic measuring tools, and extraordinary patience are still useful to astronomers today who have access to space telescopes and supercomputers. There's something humbling about the continuity of that scientific tradition, the careful work of ancient sky watchers forming a bridge across thousands of years to inform our current understanding of planetary motion. The Chinese approach to Mercury was perhaps the most philosophically sophisticated. They called it Shui Xing, the water star, connecting it to their 5-element system where each visible planet represented one of the fundamental forces that shaped the world. Mercury's association with water wasn't based on any knowledge of actual water on the planet. That discovery would wait until the 21st century, but on water's symbolic properties of adaptability, change, and swift movement. If you've ever watched water flow around obstacles in a stream, constantly changing course but never stopping, never pausing, always finding a way forward, You can see why Mercury reminded Chinese astronomers of this element. Mercury never sits still in one part of the sky like Mars or Jupiter might. It's always moving, always changing its relationship to the Sun, always appearing in a slightly different guise. Like water, it's predictable in its general behavior, but endlessly variable in its specific manifestations. Perhaps the most remarkable thing about these ancient discoveries is how they happened at all. Mercury is genuinely difficult to observe, even with modern equipment. It's never visible for more than a few hours at a time, and only when atmospheric conditions are just right. The fact that people working without telescopes, in an era before electric lights washed out the night sky, could track this elusive planet with enough precision to recognize its true nature, speaks to something wonderful about human curiosity and persistence. These weren't professional astronomers in our modern sense. They were priests, farmers, navigators, and curious individuals who simply made time in their lives to look up and wonder. They developed their understanding through the accumulated observations of generations, each sky watcher building on the work of those who came before, slowly assembling a picture of Mercury's true behavior through patient attention to its shy appearances in dawn and twilight skies. And here's where we circle back to that original experience of trying to spot Mercury yourself. When you're standing outside in the pre-dawn darkness, scanning the eastern horizon for that telltale bright point of light, you're participating in the same fundamental act of observation that fascinated ancient peoples around the world. The Mercury you're looking for is the same Mercury that puzzled Greek philosophers, inspired Babylonian priest astronomers, and challenged Chinese scholars to think deeply about the nature of change and permanence in the cosmos. The only difference is that now we know why Mercury plays its games of appearance and disappearance. We understand that its swift 88-day orbit around the Sun creates the complex pattern of visibility that so intrigued our ancestors. We can predict exactly when Mercury will next be visible from any location on Earth, and we can explain why it sometimes seems to slow down, stop, and even move backward against the background stars. But knowing the mechanism doesn't diminish the magic, does it? If anything, understanding Mercury's orbital dance makes its appearances even more special. When you catch sight of it hanging there in the twilight, whether at dawn or dusk, you're witnessing the same cosmic ballet that has been playing out for billions of years. The same performance that inspired some of humanity's earliest scientific thinking and most enduring mythologies. The ancient names for Mercury, Hermes, Apollo, Nabu, Shui-Xing, echo down through the centuries as reminders of our species' long relationship with this elusive messenger. Each culture that noticed Mercury's distinctive behavior added their own interpretation to the story, but they all recognize something essential about this planet. It's special. It moves differently, appears differently, behaves differently from all the other wandering stars. In that sense, Mercury was our first teacher in the art of careful observation and patient interpretation. It showed our ancestors that the sky holds mysteries that can only be solved through sustained attention and thoughtful analysis. The lesson Mercury taught, that things are not always what they first appear to be, became one of the foundational principles of scientific thinking. So the next time Mercury makes one of its rare appearances in your sky, perhaps you'll think of all the eyes that have searched for it before yours, all the minds that have puzzled over its behavior, all the cultures that have given it names and stories. You're joining a conversation that has been going on for thousands of years, adding your own moment of wonder to humanity's long relationship with the swift messenger of the dawn. And if you do manage to spot it, that bright, steady point of light hanging in the twilight, take a moment to appreciate the journey it's taken to reach your eyes. The photons hitting your retina have travelled nearly 100 million kilometres from Mercury's sun-baked surface, carrying information about temperature, composition and motion across the vast emptiness of space. You're not just seeing a planet, you're receiving a message that left its source just minutes ago, the latest in an unbroken chain of communications between Mercury and Earth that has been running for as long as both worlds have existed. There's something almost magical about that connection, standing on Earth, feeling the solid ground beneath your feet, the familiar atmosphere around you, looking across the solar system to a world so different from your own that it might as well be from another universe entirely. Yet there it is, visible to your unenhanced human eye, close enough that light can bridge the gap in a few minutes, distant enough that it remains forever mysterious. Mercury has been many things to many people: herald, messenger, mystery, puzzle, and now increasingly a destination. But perhaps most importantly, it has been a teacher, showing us that the universe is stranger and more wonderful than we might expect, that patient observation can reveal truths hidden from casual glance, and that even the smallest and most elusive of worlds has stories worth telling and secrets worth discovering. As you settle back into your comfortable position tonight, perhaps Mercury is visible somewhere in your sky, or perhaps it's hiding again, racing around the far side of the Sun on its endless swift orbit. Either way, it's out there, keeping its ancient appointment with the cosmos, ready to play its games of appearance and disappearance for anyone patient enough to look and wonder. If planets were runners in a cosmic marathon, Mercury would be that slightly manic competitor who laps everyone else while barely breaking a sweat. While Earth plods along in its steady year-long orbit, Mercury zips around the Sun not once, not twice, but more than 4 times. By the time you've experienced all 4 seasons and blown out your birthday candles, Mercury has celebrated its birthday 4 times over and is well into its 5th year. It's almost unfair, really, like watching someone else's calendar run at fast-forward speed while yours maintains its sensible, measured pace. This extraordinary speed isn't just a curious fact to file away in the interesting space trivia category of your mind. Mercury's swift orbital dance tells us profound stories about gravity, motion, and the fundamental laws that govern how worlds move through space. Every 88 days, Mercury completes another lap around the Sun, making it not just the closest planet to our star, but also the fastest. And here's where things get beautifully complicated. That speed isn't constant. Mercury doesn't cruise along at a steady pace like a car on a highway. Instead, it swoops and slows in an elegant rhythm that would have delighted ancient astronomers if they could have seen it clearly enough to measure. Picture Mercury's orbit as an elongated oval rather than a perfect circle. At one end of this oval, Mercury races past the Sun at its closest approach, a point astronomers call perihelion, getting as near as 46 million kilometres to our star. That might still sound like an enormous distance, and it is by human standards, but in astronomical terms, Mercury at perihelion is practically skimming the Sun's surface. For comparison, Earth maintains a relatively comfortable 150 million kilometres from the Sun year-round, more than 3 times Mercury's closest approach. At perihelion, Mercury is absolutely flying. It reaches speeds of nearly 59 kilometers per second. That's fast enough to travel from New York to Los Angeles in about a minute. The Sun looms enormous in Mercury's sky at this point, appearing nearly twice as large as it does when Mercury is at its most distant point. If you could somehow stand on Mercury's sun-baked surface during perihelion passage, the Sun would fill a significant portion of the sky, a blazing disk so brilliant and close that it would dominate your entire visual field. But here's where Mercury's orbital dance becomes particularly graceful. As it swings around the Sun and begins to move away again, it gradually slows down. By the time it reaches the far end of its orbit, aphelion, at about 70 million kilometers from the Sun, Mercury has decelerated to a more sedate 39 kilometers per second. It's still moving faster than any other planet in the solar system, but compared to its perihelion sprint, this feels almost leisurely. This variation in speed isn't just a quirky characteristic of Mercury's orbit, it's a perfect demonstration of one of the most fundamental laws of planetary motion. Johannes Kepler, working in the early 1600s with observations made by his mentor, Tycho Brahe, discovered that planets move faster when they're closer to the Sun and slower when they're farther away. What Kepler couldn't have known is that this happens because of the way gravity works. As Mercury falls toward the Sun during its approach, gravity accelerates it, much like a ball rolling down a hill picks up speed. As it swings around and starts to climb back up the gravitational hill, it naturally slows down again. You can experience a version of this yourself if you've ever been on a playground swing. When you're at the bottom of your arc, you're moving fastest. At the top of each swing, you slow down almost to a stop before falling back the other way. Mercury's orbit works on the same principle, except instead of swinging back and forth, it's following an elliptical path around the Sun, speeding up and slowing down in an endless gravitational dance that has been going on for over 4 billion years. But Mercury's orbital mechanics hold an even more elegant secret, one that eluded astronomers for centuries and ultimately required Einstein's revolutionary thinking to fully understand. If you could somehow hover above the solar system and watch Mercury's orbit over many years, speeded up like a time-lapse movie, you would notice something peculiar. The elliptical orbit itself slowly rotates, like a spinning oval drawn on a cosmic blackboard. The point of Mercury's closest approach to the Sun gradually shifts position, tracing out a slow rosette pattern over time. This phenomenon, called the precession of perihelion, was a genuine mystery in 19th century astronomy. Newton's laws of gravity could account for most of Mercury's orbital behavior beautifully, but they couldn't quite explain this slow rotation of the orbit itself. The discrepancy was tiny. Mercury's perihelion advanced by only 43 arcseconds per century, more than Newton's laws predicted. To put that in perspective, 43 arcseconds is about the angular size of a coin viewed from a kilometre away. It's unimaginably small, yet it was measurable, and it was wrong according to the best physics of the time. Astronomers tried everything they could think of to explain this discrepancy. Maybe there was an undiscovered planet closer to the Sun, tugging on Mercury with its gravity. They even gave this hypothetical planet a name, Vulcan, and spent decades searching for it. Maybe the Sun wasn't perfectly spherical, or maybe Newton's law of gravity needed a tiny correction. But none of these explanations worked. The mystery of Mercury's precessing orbit remained unsolved for decades, a small but persistent thorn in the side of classical physics. Enter Albert Einstein in 1915 with his newly developed theory of general relativity. Einstein proposed that what we experience as gravity isn't really a force pulling objects together, but rather the curvature of space and time itself around massive objects. In this view, the Sun doesn't pull Mercury toward it. Instead, the Sun's tremendous mass warps the fabric of space-time, and Mercury simply follows the straightest possible path through this curved space, which appears to us as an elliptical orbit. When Einstein applied his new theory to Mercury's orbit, something remarkable happened. The equations naturally predicted exactly the amount of perihelion precession that astronomers had been measuring. the mysterious 43 arcseconds per century fell out of the mathematics like a ripe fruit, requiring no additional assumptions or adjustments. It was one of those moments in physics where theory and observation clicked together with almost audible satisfaction. This wasn't just a victory for Einstein's theory. It was a profound validation of the idea that our understanding of the universe could be deepened by questioning our most basic assumptions about space, time, and gravity. Mercury, the smallest and swiftest planet, had become an unwitting test case for one of the most important theories in the history of science. Its tiny orbital deviation helped confirm that we live in a universe stranger and more beautiful than Newton had imagined, a universe where space and time are woven together in a flexible fabric that massive objects can stretch and curve. The story of Mercury's orbital mechanics doesn't end with Einstein, though. Modern spacecraft tracking has revealed even more subtle details about how Mercury moves through space. We now know that Mercury's orbit is also influenced by the gravitational tugs of Venus, Earth, and the other planets, creating tiny variations that require supercomputers to calculate precisely. We've measured how the Sun's own motion through space affects Mercury's path, and how the gradual loss of mass from the Sun through solar wind creates minor changes in Mercury's orbital period. Perhaps most fascinating of all, we've discovered that Mercury's rapid orbit makes it an excellent natural laboratory for testing our understanding of gravity in extreme conditions. Because Mercury experiences the Sun's gravitational field more intensely than any other planet, it serves as a cosmic test bed for theories about how gravity works in strong fields. If our theories are going to break down anywhere, Mercury's orbit is where we'd expect to see the first signs. This makes Mercury something like the canary in the coal mine of gravitational physics. Any deviation from our predictions, any tiny discrepancy between theory and observation, might signal the need for new physics, perhaps a modification of general relativity, or maybe a hint that there are additional forces at work in the universe that we haven't discovered yet. So far, Mercury has been remarkably well behaved, following Einstein's predictions with extraordinary precision. But astronomers continue to monitor its orbit with ever-increasing accuracy, ready to detect any anomaly that might point toward new discoveries. There's something almost poetic about the fact that Mercury, the planet closest to the Sun and therefore experiencing the most extreme conditions in our solar system, should also be the one that helped us understand the true nature of gravity. It's as if the universe arranged this smallest world to be both a messenger, carrying information about orbital mechanics and gravitational physics, and a teacher, showing us through its own motion how space and time really work. When you think about it, Mercury's swift dance around the Sun embodies some of the most profound concepts in modern physics, while remaining elegantly simple in its basic pattern. An elliptical orbit that speeds up when close to the Sun and slows down when farther away. It's the kind of motion you could demonstrate with a ball on a string, yet it reveals truths about the fundamental structure of reality that took humanity centuries to discover and understand. The next time you catch sight of Mercury in your twilight sky, remember that you're looking at our solar system's most devoted student of gravity. For over 4 billion years, it has been tracing its swift ellipse around the Sun, following the curvature of space-time with mathematical precision, serving as an unwitting probe of the deepest laws of physics. Every 88 days, it completes another perfect demonstration of how worlds move through the cosmos, a lesson written in orbital mechanics that astronomers are still learning to read. And perhaps there's something we can learn from Mercury's approach to its cosmic journey. It doesn't fight against the laws that govern its motion, it embraces them, following the path that space-time provides with elegant efficiency. It speeds up when conditions call for acceleration, slows down when the universe asks for patience, and maintains its course through whatever gravitational influences come its way. In its own swift, silent way, Mercury might just be showing us how to dance gracefully with the forces that shape our lives, not by resisting them, but by understanding their rhythm and moving in harmony with their flow. Mercury continues its ancient dance, 88 days at a time, keeping perfect time to the gravitational music of the spheres. In its swift passage around the Sun, it carries with it the secrets of orbital mechanics and the whispered lessons of Einstein's curved space-time, a small world that has taught us some of the biggest truths about how the universe really works. Imagine trying to describe Mercury to someone who has never heard of it before. You might start with its size, mentioning that it's about as wide as the United States, which sounds impressively large until you realize that makes it smaller than some of the moons orbiting Jupiter and Saturn. You could mention that it's the closest planet to the Sun, which conjures images of a blazing inferno, then add that parts of it are permanently frozen, which would probably leave your listener wondering if you'd gotten confused about which planet you were describing. Mercury has this wonderful way of defying easy categorization, presenting us with a world that seems almost designed to challenge our assumptions about what planets should be like. The first thing that strikes most people when they see an accurate scale model of Mercury next to Earth is just how small it really is. If Earth were a basketball sitting on your desk, Mercury would be a tennis ball placed about 100 meters away. It's not just smaller in diameter, though at roughly 4,880 kilometers across, it's less than 40% the width of Earth. It's also much less massive. You could fit about 18 Mercuries inside Earth by volume, but it would take more than 18 of them to equal Earth's mass, because Mercury is surprisingly dense for such a small world. This density tells us something fascinating about Mercury's internal structure. Most of Mercury, about 75% of its radius, is taken up by an enormous iron core. If you could slice Mercury open like an apple, you'd find that it's more like a cannonball with a thin shell than a typical rocky planet. Earth's iron core, by comparison, makes up only about 55% of our planet's radius. Mercury is essentially a giant ball of metal with just enough rock around the outside to give it a proper planetary appearance. Why Mercury ended up with such an outsized core remains one of the more intriguing mysteries in planetary science. One possibility is that Mercury formed much like the other terrestrial planets, with a normal mix of rock and metal, but then suffered a catastrophic collision early in its history. This hypothetical impact might have blasted away much of Mercury's rocky mantle, leaving behind a world that's mostly core, with just a thin veneer of the original surface material. It's a violent origin story for such a small world, but it would explain why Mercury seems to be built so differently from its planetary siblings. Another possibility is that Mercury formed in a region of the early solar system, where temperatures were so high that rocky materials simply couldn't condense effectively. In this scenario, only the most refractory materials, those that can withstand extreme heat, would have been available to build planets so close to the Sun. Iron and nickel, being among the most heat-resistant planetary building blocks, would have dominated the construction materials available in Mercury's neighborhood. The result would be a world naturally enriched in metals, even without any dramatic collision to strip away lighter materials. Standing on Mercury's surface, if you could somehow manage such a feat, you would immediately notice something that no amount of description can fully prepare you for. The gravity feels strangely light. At only 38% of Earth's gravity, every movement would feel like a gentle dance. You could jump nearly 3 times higher than on Earth, and objects would fall with a dreamy slowness that would make even the clumsiest person feel graceful. A baseball thrown on Mercury would arc through the sky in a long, lazy parabola that would seem to hang in the air forever compared to the same throw on Earth. But the low gravity would be the least of your concerns on Mercury's surface. The real challenge would be the temperature, and here's where Mercury reveals its truly extreme nature. During the day, surface temperatures can reach 427 degrees Celsius, hot enough to melt zinc, tin, and lead. If you somehow found yourself on Mercury's sun-facing side, you wouldn't just feel hot, you would literally be cooked by the radiant heat from the ground beneath your feet. The rocks themselves would glow with thermal radiation, turning the entire landscape into a vast natural oven. Yet turn to Mercury's night side, and you'd encounter conditions almost equally extreme in the opposite direction. Without any atmosphere to trap and redistribute heat, Mercury's night side plunges to temperatures around -170 degrees Celsius. That's cold enough to freeze carbon dioxide solid and turn any remaining wisps of atmosphere into a thin coating of frost on the rocks. The temperature difference between Mercury's day and night sides, nearly 600 degrees Celsius, is the most extreme found anywhere in the solar system. This dramatic temperature swing happens because Mercury essentially has no atmosphere to speak of. When we say no atmosphere, we don't mean a thin atmosphere like Mars has, or even a trace atmosphere like the Moon. Mercury's atmospheric pressure is less than 1/1,000,000th of Earth's, so tenuous that it's barely distinguishable from the vacuum of space itself. If you could somehow stand on Mercury's surface without a spacesuit, you wouldn't suffocate from lack of oxygen. You would die instantly from the near-perfect vacuum, your blood literally boiling in your veins as the pressure dropped to almost nothing. The reason Mercury can't hold on to an atmosphere has everything to do with its size, its proximity to the Sun, and the relentless solar wind that streams away from our star at all times. Small worlds have weak gravity, which makes it difficult to hold on to atmospheric gases in the first place. Add to that the intense heating from being so close to the Sun, which gives gas molecules more energy to escape, and you have a recipe for atmospheric loss. But the final blow comes from the solar wind itself, a stream of charged particles flowing away from the Sun at hundreds of kilometers per second. On Earth, our magnetic field deflects most of the solar wind, creating a protective bubble around our planet that shields our atmosphere from being stripped away. Mercury does have a magnetic field, but it's only about 1% as strong as Earth's. Barely enough to deflect some of the solar wind, but not enough to provide real protection for an atmosphere. Over billions of years, any atmosphere Mercury might have had has been steadily eroded away by this combination of weak gravity, intense solar heating, and the relentless blast of solar particles. What little atmosphere Mercury does have is constantly being replenished and constantly being lost in a dynamic balance that changes with the planet's position in its orbit. When Mercury is closer to the Sun, the solar wind hits harder and strips away atmospheric particles faster. When it's farther away, the rate of loss decreases, allowing a slightly thicker atmosphere to build up temporarily. It's like trying to fill a bucket with a huge hole in the bottom. You can keep adding water, but you'll never accumulate very much. The source of Mercury's thin atmosphere is itself rather remarkable. Some of it comes from the solar wind itself, particles from the Sun that get temporarily captured by Mercury's weak magnetic field before escaping again. Some comes from the slow vaporization of surface rocks under the intense solar heating, and some may come from micrometeorite impacts that blast tiny amounts of surface material into space, where it briefly joins Mercury's tenuous atmospheric envelope before being swept away by the next solar wind gust. This constant recycling of atmospheric material makes Mercury's thin atmosphere one of the most dynamic in the solar system, even though it's also one of the most sparse. The composition changes depending on which part of the surface is being heated most intensely, which meteorites might have hit recently, and how strong the solar wind happens to be at any given moment. It's an atmosphere in constant flux, never the same from one day to the next. The absence of any significant atmosphere also means that Mercury experiences no weather as we would understand it. There are no winds to stir up dust storms, no temperature gradients to drive circulation patterns, no seasonal changes to create variety in atmospheric conditions. The only sounds on Mercury would be those transmitted through the solid rock itself, the creaking and groaning of thermal expansion as rocks heat and cool, the occasional impact of a meteorite, perhaps the settling sounds of landslides in areas where thermal stress has weakened cliff faces. Yet in this apparent desolation, Mercury holds some surprises that remind us how much we still have to learn about even our nearest planetary neighbours. Despite the intense solar heating, despite the lack of atmosphere, despite surface temperatures that can melt metal, Mercury somehow manages to harbour water ice in permanently shadowed regions near its poles. These deposits, hidden in craters that never see direct sunlight, represent one of the most unexpected discoveries in recent planetary science. The ice exists because of Mercury's almost upright orientation relative to its orbit. Unlike Earth, which tilts about 23 degrees and therefore experiences seasons, as different parts of the planet receive varying amounts of sunlight throughout the year. Mercury's rotational axis is tilted by only about 2 degrees. This means that the bottoms of deep craters near Mercury's poles can remain in permanent shadow, creating natural freezers where temperatures stay cold enough to preserve water ice for billions of years. Finding ice on Mercury is a bit like discovering snow in the middle of the Sahara Desert. Theoretically possible under exactly the right conditions, but so unexpected that it challenges our intuitive understanding of how planetary environments work. The ice probably arrived via comet impacts over Mercury's long history, with each impact delivering a small amount of water that would normally be vaporized instantly by the intense solar radiation. But in those permanently shadowed polar regions, some of that water found refuge from the sun's heat and accumulated into deposits that may be several meters thick in places. This discovery transforms our understanding of Mercury from a simple, dead rock baking in the sun's heat to a more complex world with its own unique environmental niches. It suggests that even under the most extreme conditions, water, that essential ingredient for life as we know it, can find ways to persist. While Mercury itself is far too harsh to support any known form of life, the presence of water ice expands our thinking about where we might find such resources in other extreme environments throughout the solar system. Mercury's extreme characteristics make it something like a natural laboratory for understanding how planetary physics works under the most challenging conditions our solar system can provide. Its enormous core gives us insights into planetary formation and the role of early impacts in shaping worlds. Its lack of atmosphere helps us understand atmospheric evolution and the importance of magnetic fields in protecting planetary environments. Its extreme temperature variations show us what happens when a world has no moderating influences, no atmosphere to redistribute heat, no large moon to stabilize its rotation, no weather patterns to smooth out temperature differences. In many ways, Mercury represents the stripped-down essence of what it means to be a terrestrial planet. Without the complications of atmosphere, weather, oceans, or life, it shows us planetary physics in its purest form. The laws of thermodynamics, orbital mechanics, and electromagnetic radiation play out on Mercury's surface with mathematical clarity, unobscured by the complex interactions that make Earth's environment so rich, but also so difficult to understand completely. There's something almost Zen-like about Mercury's extremes, the way it embraces the full range of temperatures possible for a rocky world, the way it maintains its swift orbit despite being pulled so strongly by the sun's gravity, the way it preserves ancient ice in the midst of blazing heat. It's a world that has found stability, not by avoiding extremes, but by incorporating them into its very nature. As you settle into your comfortable position tonight, perhaps you can imagine what it might be like to experience Mercury's gentle gravity, to see the sun looming enormous in its black sky, to stand at the boundary between blazing day and frozen night on this most extreme of worlds. It's a planet that reminds us that the universe is full of places stranger and more wonderful than our Earth-based experience might lead us to expect. Worlds where the impossible becomes routine and the extreme becomes simply another way of being. If you've ever looked at photographs of Mercury's surface, your first impression might be that someone has been playing cosmic darts for billions of years, using the planet as their target board. Mercury's face is absolutely peppered with craters, small ones, medium ones, enormous ones that could swallow entire countries, and countless tiny pockmarks that blur together into a textured landscape that tells one of the most violent stories in our solar system. Unlike Earth, where weather and geological activity constantly erase and remake the surface, Mercury has kept a nearly perfect record of every cosmic punch it has taken over the past 4 billion years. There's something almost melancholy about Mercury's cratered face when you really study it. Each crater represents a moment of tremendous violence, a chunk of rock or metal, perhaps the size of a mountain or a city, hurtling through space at tens of kilometers per second before smashing into Mercury's surface with the force of thousands of nuclear weapons. The impact would have lasted only seconds, but the scar it left behind has persisted for eons, a permanent memorial to a collision that happened when the solar system was young and chaotic. The largest and most impressive of these ancient scars is the Caloris Basin, a massive crater that stretches about 1,550 kilometers across Mercury's surface. To put that in perspective, if Caloris Basin was centered on Chicago, its rim would reach past Denver to the west and beyond New York City to the east. It's so large that when Mercury rotates, it takes hours for the entire basin to pass, from the day side to the night side of the planet. The impact that created Caloris must have been absolutely catastrophic, the kind of collision that briefly turned a significant portion of Mercury's surface into a sea of molten rock and sent shock waves reverberating through the entire planet. What makes Caloris even more fascinating is what it tells us about Mercury's early history. The impactor that created this basin was probably an asteroid tens of kilometers across, possibly larger than the one that ended the age of dinosaurs on Earth. When it struck Mercury, it would have excavated an enormous amount of material, hurling rocks and debris across thousands of kilometers of the planet's surface. Some of this material fell back down as secondary impacts, creating chains and clusters of smaller craters around the main basin. Other material was blasted completely off the planet, adding to the collection of rocks and dust that orbits throughout the inner solar system. But perhaps the most remarkable aspect of the Caloris impact is what it did to the opposite side of Mercury. The shock waves from the collision travelled through the planet's rocky interior, converging on the point directly opposite the impact site. When these waves met, they created a strange, chaotic landscape that astronomers call the weird terrain, a jumbled region of hills, valleys, and broken ground unlike anything else on Mercury's surface. It's as if the planet itself was trying to absorb the tremendous energy of the impact, and the only way it could do so was by completely reshaping a large area on the far side of the world. Imagine the violence required to punch a hole in one side of a planet and completely scramble the landscape on the opposite side. The Caloris impact wasn't just a local event. It was a planet-wide catastrophe that left permanent scars on both sides of Mercury. Standing in the weird terrain today, if you could somehow manage such a thing, you would be standing in the echo of an impact that happened billions of years ago. A landscape shaped not by the gentle processes of erosion or volcanism, but by seismic waves that travelled clear through the planet's core and mantle before converging beneath your feet. The timing of the Caloris impact tells us something important about the early solar system. Based on the number of smaller craters that have accumulated on top of the Caloris basin since it formed, astronomers estimate that this massive collision happened about 3.8 to 3.9 billion years ago, during a period known as the Late Heavy Bombardment. This was a time when the inner planets were under constant assault from leftover debris from the solar system's formation. Asteroids and comets that hadn't yet settled into stable orbits and were careening around the inner solar system like cosmic pinballs. Earth and the Moon suffered through this same bombardment period, but most of the evidence has been erased from Earth's surface by billions of years of weathering, plate tectonics, and biological activity. The Moon preserves more of this ancient history, but even there, later impacts and the gradual rain of micrometeorites have softened and obscured many of the oldest features. Mercury, with its lack of atmosphere and geological stillness, has maintained the most complete record of this violent chapter in solar system history. Looking at Mercury's crater-covered surface is like reading a book written in impacts, with each crater representing a different chapter in the story of cosmic bombardment. The largest craters, like Caloris, tell us about the biggest players in this ancient drama, the massive asteroids whose impacts reshaped entire regions of the planet. Medium-sized craters, perhaps 50 to 100 kilometers across, speak to the more routine violence of smaller but still significant impacts, and the countless tiny craters that pepper every square kilometer of Mercury's surface record the steady rain of debris that has continued at a much reduced rate right up to the present day. One of the most intriguing aspects of Mercury's crater record is how well it has been preserved. On Earth, a crater the size of Caloris would have been erased by erosion, filled in by sediments, or broken up by tectonic activity long ago. Even the famous Chicxulub crater that marks the impact that killed the dinosaurs is barely visible today, detectable mainly through subtle gravitational anomalies and core samples that reveal the telltale signature of impact debris. Mercury's craters, by contrast, look almost as fresh as the day they were formed. The rims are still sharp, the central peaks still stand tall, and the rays of debris that were blasted out during the impact are still visible, streaking across the landscape. It's a bit like walking through a museum of cosmic violence, where every exhibit has been perfectly preserved for billions of years. The largest craters have been somewhat modified by later impacts, and by the slow process of thermal expansion and contraction that comes with Mercury's extreme temperature swings, but even these changes are minimal compared to what would happen on a more geologically active world. This preservation of impact features makes Mercury an invaluable laboratory for understanding how impacts work and what they can tell us about the history of the solar system. By studying the size distribution of Mercury's craters, astronomers can reconstruct the population of asteroids and comets that were flying around the inner solar system during different periods in the past. Larger craters are rarer because the asteroids capable of creating them were rarer. Smaller craters are more common because there were many more small impactors than large ones. The pattern is remarkably consistent across all the terrestrial planets, suggesting that they all experience the same basic bombardment history. This gives us confidence that we're seeing evidence of a genuine solar system-wide event, not just random bad luck for one particular planet. The late heavy bombardment appears to have been a time when something, perhaps gravitational interactions between the giant planets, stirred up the asteroid belt and sent a shower of debris toward the inner planets. Some of Mercury's craters also preserve evidence of the conditions that existed when the impacts occurred. Young craters often have bright rays of material extending outward from the impact site, similar to the ray systems around lunar craters like Copernicus or Tycho. These rays consist of fresh material that was excavated and thrown outward during the impact, creating streaks of relatively unweathered rock that reflect sunlight more brightly than the surrounding terrain. On Mercury, the youngest craters with the most prominent ray systems probably formed within the last few 100 million years, recent by geological standards, but still ancient by human measures. The fact that these rays are still visible tells us something about how slowly Mercury's surface changes. There's no wind to redistribute dust, no rain to wash away the bright streaks, no vegetation to grow over the impact debris. The rays fade very slowly, darkened only by the gradual accumulation of micrometeorite dust and the subtle effects of solar radiation breaking down the surface minerals. Perhaps even more fascinating are Mercury's lobate scarps, long curving cliff faces that snake across the planet's surface for hundreds of kilometers. These aren't impact features at all, but rather evidence that Mercury has been slowly shrinking over geological time. As the planet's interior cooled and contracted, the surface was forced to wrinkle and fold, creating these thrust faults where one section of crust has been pushed up and over another. The lobate scarps cut across many of Mercury's craters, indicating that the planet's contraction has continued long after the main period of bombardment ended. Some scarps even cut across relatively young craters, suggesting that Mercury's interior is still cooling, and that the planet may still be shrinking by tiny amounts today. It's a reminder that even apparently dead worlds can harbour subtle geological processes that play out over enormous timescales. The interplay between impacts and tectonic activity on Mercury creates a landscape that's both ancient and dynamic. The basic framework of large basins and crater chains was established billions of years ago during the late heavy bombardment, but the details continue to evolve as the planet slowly contracts and newer impacts add their own signatures to the mix. It's like looking at a palimpsest, an ancient manuscript where multiple texts have been written one over the other, each layer adding to the story but never completely erasing what came before. When spacecraft first began photographing Mercury's surface in detail, starting with Mariner 10 in the 1970s and continuing with the Messenger mission in the 2000s and 2010s, the images revealed a world that was both familiar and alien. Familiar because the basic pattern of overlapping craters resembled what we see on the Moon, but alien because of the subtle differences in how those craters had been shaped by Mercury's unique environment. Mercury's stronger gravity means that impact debris doesn't travel as far from the point of impact as it would on the Moon. This creates craters with relatively compact ejecta patterns and steeper rim slopes. The extreme temperature variations on Mercury also mean that rocks expand and contract more dramatically than they would in the Moon's more moderate thermal environment, leading to different patterns of weathering and erosion around crater rims and walls. These subtle differences help planetary scientists understand not just Mercury's history, but the general principles of how impacts work under different conditions. Every crater on Mercury is a natural experiment in impact physics, providing data about how factors like gravity, atmospheric pressure, and thermal environment affect the outcome of cosmic collisions. There's something both humbling and comforting about Mercury's ancient scars. Humbling because they remind us of the violent forces that shaped our solar system and continue to operate today. Forces so powerful that they can excavate basins the size of countries and send shockwaves through entire worlds. But also comforting because they demonstrate the incredible stability and endurance of rocky planets like Mercury. Despite billions of years of bombardment, despite impacts that would make human disasters look trivial by comparison, Mercury has survived. It has absorbed every punch the cosmos has thrown at it and maintained its orbit, its basic structure, its essential character as a world. In Mercury's pockmarked face, we see not just destruction, but preservation, the careful keeping of a record that stretches back to the solar system's youth. Each crater is both an ending and a beginning, the end of an asteroid's billion-year journey through space, and the beginning of a new chapter in Mercury's geological story. The scars may speak of violence, but they also speak of endurance, resilience, and the quiet persistence of worlds that outlast the catastrophes that shape them. As Mercury continues its swift orbit around the Sun, it carries with it this ancient library of impacts, each crater a book waiting to be read by future explorers, who will one day walk among these silent monuments to cosmic history. Until then, Mercury keeps its vigil, turning its scarred face toward the Sun each day, a living museum of the solar system's violent and magnificent past. Sometimes the universe has a sense of humor that borders on the absurd. Consider for a moment the idea of searching for ice on a planet where the ground can get hot enough to melt lead. It's rather like expecting to find penguins in the Sahara Desert or discovering snow in a furnace. Yet that's exactly what happened when astronomers began seriously studying Mercury's polar regions in the 1990s. What they found there was so unexpected, so contrary to everything our intuition tells us about the closest planet to the Sun, that it fundamentally changed how we think about where water can exist in the solar system. The story of ice on Mercury begins with an odd observation made by radio astronomers using the Arecibo telescope in Puerto Rico. They were bouncing radar signals off Mercury's surface, a technique that allows scientists to map the topography and composition of planetary surfaces from Earth. Most of the reflected signals behaved exactly as expected, creating detailed maps of Mercury's craters and plains. But in certain areas near Mercury's north and south poles, the radar signals came back unusually bright and with a distinctive polarization signature that radio astronomers had learned to associate with one thing: water ice. The initial reaction to this discovery was, understandably, skepticism. Mercury, after all, is the planet that spends its days baking in temperatures that would vaporize water instantly. The idea that solid ice could exist anywhere on its surface seemed to violate everything we thought we knew about this sun-scorched world. Some scientists suggested that the bright radar returns might be caused by unusual rock formations or perhaps deposits of some exotic mineral that happen to reflect radio waves in a similar way to ice. But as more observations accumulated, the evidence became harder and harder to dismiss. The bright areas were found exclusively in the deepest parts of craters near Mercury's poles, exactly the locations where ice would be most likely to survive if it existed anywhere on the planet. The radar signatures matched those of known ice deposits on other worlds almost perfectly. And when scientists calculated the temperatures in these polar crater floors, they found conditions cold enough to preserve water ice for billions of years. The key to understanding how ice can exist on Mercury lies in the planet's unusual orientation. Most planets in our solar system are tilted on their axes relative to their orbits around the Sun. Earth, for example, tilts about 23 degrees, which is what gives us our seasons, as different parts of the planet receive more or less direct sunlight throughout the year. Mercury, however, stands almost perfectly upright relative to its orbit, with an axial tilt of only about 2 degrees. This minimal tilt means that Mercury doesn't experience seasons the way Earth does, but it also creates a peculiar situation at the planet's poles. Deep craters near the north and south poles can have floors that never receive direct sunlight. Not during Mercury's 88-day year. Not during its strange 176-day solar day, not ever. These permanently shadowed regions exist in a state of perpetual winter, even while the surrounding landscape bakes in temperatures that could melt zinc. Picture standing on the rim of one of these polar craters during Mercury's blazing day. The rocks around you would be hot enough to glow with their own thermal radiation, radiating heat that you could feel from meters away. The sun would hang enormous in the black sky above, a brilliant disk 11 times larger than it appears from Earth. Yet just a few hundred meters away, down in the crater's shadowed depths, temperatures would be cold enough to freeze anything that happened to fall there. The contrast is almost surreal, a cosmic demonstration of how local conditions can vary dramatically even on the same small world. It's like having the surface of Venus and the surface of Pluto existing within walking distance of each other, separated only by the angle of sunlight and the simple physics of radiant heating and cooling. But where did the ice come from in the first place? Mercury is far too hot and airless to have any kind of water cycle that could deposit snow or frost in these polar regions. The water must have arrived from somewhere else, delivered by cosmic messengers travelling across the vast distances of the solar system. The most likely candidates are comets, those dirty snowballs that spend most of their time in the cold outer reaches of the solar system, but occasionally fall inward toward the Sun. When a comet impacts Mercury, most of its water would be vaporized instantly by the intense heat and then lost to space, but some small fraction might find its way to those permanently shadowed polar regions where it could freeze solid and remain stable for geological ages. Over billions of years, comet after comet delivering water to Mercury, most of it lost but tiny amounts accumulating in the polar cold traps, the ice deposits could grow substantial. Radar observations suggest that some of these deposits might be several meters thick in places, not exactly glaciers, but significant accumulations of water ice nonetheless. What makes this discovery even more intriguing is what it tells us about the early solar system. If Mercury has managed to accumulate and preserve water ice despite its harsh environment, it suggests that water delivery by comets was an important process throughout the inner solar system. Earth's oceans might owe their existence partly to the same process that created Mercury's modest ice deposits. Countless comet impacts over hundreds of millions of years, gradually building up the water inventory of the terrestrial planets. The Messenger spacecraft, which orbited Mercury from 2011 to 2015, provided the first definitive confirmation of the ice deposits through direct observation. Using a neutron spectrometer, Messenger could detect the hydrogen signature of water ice, even though the deposits were hidden in permanent shadow where cameras couldn't see them. The spacecraft also measured the temperatures in these shadowed regions, confirming that they were indeed cold enough to preserve ice over geological time. Perhaps even more surprisingly, Messenger discovered that the ice wasn't pure. Mixed in with the water ice were organic compounds, carbon-based molecules that are the building blocks of life as we know it. These organics probably arrived along with the water, delivered by the same comets that brought the ice. On most of Mercury's surface, such organic compounds would be broken down quickly by the intense solar radiation, but in the permanently shadowed polar regions, they can survive indefinitely. The presence of organic materials on Mercury adds another layer of cosmic irony to the story. Here's a planet so close to the Sun that its day side could melt lead, yet in its polar regions it preserves not just water ice, but also the kinds of carbon compounds that are essential for life. It's not that Mercury could ever support life, the conditions are far too extreme, but it does serve as a repository for some of the same materials that made life possible on Earth. Understanding Mercury's polar ice has implications that extend far beyond our own solar system. As astronomers discover more and more planets orbiting other stars, they're finding many that orbit much closer to their host stars than Mercury does to our Sun. These hot Jupiters and super-Earths in close orbits were once thought to be completely inhospitable to any kind of chemistry that might be relevant to life. But Mercury's ice deposits suggest that even planets in very close orbits around their stars might have cold refuges where water and organic compounds can survive, perhaps permanently shadowed polar regions or areas shielded by unusual topography could preserve the raw materials for life even on worlds that seem impossibly hostile. It's a reminder that nature is often more creative and resourceful than our imaginations. The discovery of ice on Mercury also highlights the importance of thinking about planetary environments in 3 dimensions, rather than just considering average surface conditions. Mercury's average surface temperature is indeed hot enough to vaporize water, but averages can be misleading when conditions vary so dramatically from place to place. The polar ice deposits exist in microenvironments that are completely different from the bulk of the planet's surface. This kind of environmental complexity is probably the rule rather than the exception for planets throughout the universe. Even worlds that seem uniformly hostile might harbour niches where conditions are more moderate, where interesting chemistry can occur, where the unexpected becomes possible. Mercury's polar ice is a perfect example of how local topography and orbital geometry can create islands of habitability in otherwise impossible environments. From a practical standpoint, Mercury's water ice deposits represent a potentially valuable resource for future space exploration. Water can be broken down into hydrogen and oxygen, providing both rocket fuel and breathable air for astronauts. Any human mission to Mercury would face enormous challenges from the intense heat and radiation, but the polar ice deposits could provide essential resources for life support and transportation. Mining ice from Mercury's polar regions would be technically challenging, requiring equipment that could operate in permanently shadowed areas where temperatures approach absolute zero. But the engineering problems are solvable, and the strategic value of having a water source so close to the Sun could make Mercury an important way station for deeper exploration of the solar system. There's also something aesthetically pleasing about the idea of finding ice on the hottest planet. It reminds us that the universe is full of contradictions and surprises, that our expectations based on Earth's environment often fail to capture the full range of possibilities that exist among the worlds of our solar system. Mercury's ice is a frozen reminder that nature delights in paradox. The story of Mercury's polar ice also demonstrates the power of persistence in scientific exploration. The initial radar observations were met with skepticism, and it took years of additional observations and theoretical work before the scientific community fully accepted that ice could indeed exist on Mercury. It's a reminder that extraordinary claims require extraordinary evidence, but also that extraordinary discoveries often come from looking carefully at the places where our expectations are challenged. As you settle back tonight and perhaps glance up at the sky, remember that somewhere out there, racing around the sun at incredible speed, Mercury carries its cargo of ancient ice through the blazing heat of the inner solar system. In the deepest shadows of its polar craters, water that may have travelled for millions of years as part of distant comets now lies frozen in perpetual darkness, waiting patiently for the day when human explorers might finally arrive to discover what other secrets this most paradoxical of planets has managed to preserve. It's a beautiful reminder that even in the most extreme environments, even on worlds that seem completely alien to our experience, the universe finds ways to surprise us. Mercury's ice teaches us that water, that most essential of compounds for life as we know it, can find refuge in the most unlikely places, and that sometimes the most important discoveries happen not where we expect them, but where we least expect them to be possible. Imagine waking up one morning to discover that your day had suddenly become longer than your year. Not metaphorically longer, in that exhausting way that difficult days can feel, but literally longer. 176 Earth days from sunrise to sunrise, while the planet completes its orbit around the Sun in just 88 days. This is the delightfully peculiar reality of timekeeping on Mercury, where the relationship between days and years follows rules so unusual that it took astronomers decades to figure out exactly what was happening. For the longest time, scientists believed that Mercury was tidally locked to the Sun, meaning that one side of the planet always faced the Sun while the other side remained in permanent darkness. This seemed to make perfect sense. After all, our Moon is tidally locked to Earth, always showing us the same face, and Mercury is so close to the Sun that tidal forces should be even stronger there. The idea of a Mercury with a permanent day side and a permanent night side fitted neatly into our understanding of how gravity should work in the inner solar system. But Mercury, as we've seen throughout our journey, has a talent for defying expectations. In the 1960s, radio astronomers began studying Mercury by bouncing radar signals off its surface and analysing the reflections. What they discovered was puzzling. The dark side of Mercury, the side that should have been in permanent shadow and frozen solid, was far too warm for a surface that never saw sunlight. Something was clearly wrong with the tidal locking theory. The answer came in 1965 when astronomers Gordon Pettengill and Rolf Dice used the Arecibo radio telescope to make precise measurements of Mercury's rotation. What they found was revolutionary. Mercury wasn't locked to the Sun at all. Instead, it was rotating on its axis once every 58.6 Earth days, completing exactly 3 rotations for every 2 orbits around the Sun. This 3-to-2 resonance, as astronomers call it, creates one of the most unusual day-night cycles in the solar system. To understand how strange Mercury's days really are, you need to think about the relationship between rotation and orbit in a way that our Earth-based experience doesn't prepare us for. On Earth, we're used to a simple relationship. The planet rotates once every 24 hours, creating our familiar cycle of day and night, while it orbits the Sun once every 365.25 days, creating our year. The day and the year are completely separate phenomena, governed by different aspects of Earth's motion. On Mercury, the situation is far more complex. The planet's rotation and its orbit are locked together in a gravitational dance that creates a day length unlike anything we experience on Earth. A Mercury day, the time from one sunrise to the next sunrise at the same location, lasts 176 Earth days, exactly twice as long as Mercury's 88-day year. This means that Mercury experiences 2 complete years between one sunrise and the next. But here's where things get even stranger. Because Mercury's orbit is highly elliptical, its speed around the Sun varies dramatically depending on where it is in its orbit. When Mercury is closest to the Sun at perihelion, it's moving so fast in its orbit that its orbital motion actually overtakes its rotation. This creates a phenomenon that would seem impossible to anyone who has only experienced Earth's sky. The Sun appears to slow down, stop, reverse direction, and then resume its original course across Mercury's sky. Picture yourself standing on Mercury's surface during one of these double sunrise events. The Sun rises slowly in the east, growing larger and brighter as Mercury approaches perihelion. But then, as Mercury's orbital speed increases, the Sun appears to pause in its journey across the sky. For several Earth days, the Sun hovers nearly motionless overhead, before beginning to move backward toward the eastern horizon. It partially sets in the east, only to rise again and resume its westward journey across the sky with even greater intensity than before. This celestial choreography happens because Mercury's rapid orbital motion during perihelion passage temporarily overwhelms its rotation. It's as if the planet is racing around the Sun so quickly that it can't keep up with its own spin, causing the apparent motion of the Sun in Mercury's sky to reverse direction. The effect lasts for several days, and would be one of the most spectacular sights in the solar system for any observer fortunate enough to witness it. The physics behind Mercury's unusual rotation involves a concept called tidal locking, but not the simple kind that keeps our moon always showing the same face to Earth. Instead, Mercury has achieved what astronomers call a resonant lock, where its rotation period is precisely synchronized with its orbital period in a ratio of 3:2. This resonance is stable because it represents a minimum energy state for the Mercury-Sun system. Long ago, when Mercury was young and the solar system was still settling into its current configuration, Mercury probably rotated much faster than it does today. But the Sun's powerful gravitational field created tidal bulges in Mercury's crust, and the friction between these bulges and Mercury's rotation gradually slowed the planet's spin. In most cases, this process would eventually lead to complete tidal locking, where the planet's rotation matches its orbital period exactly. But Mercury's highly elliptical orbit prevented this from happening. The changing distance from the Sun and the varying strength of tidal forces at different points in the orbit created a more complex gravitational environment. Instead of settling into a 1-to-1 lock, Mercury found a stable configuration at 3:2, rotating 3 times for every 2 orbits around the Sun. This resonant relationship means that every location on Mercury experiences day and night, but on a schedule that would seem impossibly strange to Earth dwellers. If you could set up camp at a particular spot on Mercury's surface, you would experience about 88 Earth days of continuous daylight, followed by 88 Earth days of continuous darkness. The transition between day and night would be gradual, taking place over several Earth days as the Sun slowly set or rose. During the long day, you would watch the Sun follow a complex path across the sky, sometimes speeding up, sometimes slowing down, and occasionally performing its backwards dance during perihelion passage. The Sun would appear to change size noticeably as Mercury's distance from the Sun varied throughout its orbit, appearing nearly twice as large at perihelion as at aphelion. The temperature variations during Mercury's long day-night cycle are as extreme as you might expect. During the 88-day daylight period, surface temperatures climb steadily to over 400 degrees Celsius, hot enough to melt lead. During the 88-day night, temperatures plummet to around minus 170 degrees Celsius, cold enough to freeze carbon dioxide solid. The transition between these temperature extremes happens gradually, over the course of several Earth days as sunrise or sunset approaches. This creates a complex thermal environment where different parts of Mercury's surface are always in different phases of heating and cooling. While one region bakes in the intensity of an 88-day summer, another region on the opposite side of the planet endures an equally long winter. Areas near the terminator, the boundary between day and night, experience the relatively mild conditions of perpetual dawn or dusk. The strange relationship between Mercury's rotation and orbit also creates what astronomers call hot poles, specific points on Mercury's surface that receive maximum solar heating during perihelion passage. Because Mercury's orbit is oriented in a particular way relative to its rotation axis, these hot poles experience the most intense solar radiation in the entire solar system. Standing at one of these locations during perihelion passage would subject you to a solar flux nearly 11 times more intense than what Earth receives. For early astronomers trying to understand Mercury's behavior, the 3:2 resonance explained many puzzling observations. It accounted for why radar measurements showed the dark side of Mercury to be warmer than expected, because there is no permanently dark side. It explained the complex pattern of radio emissions from Mercury's surface, which varied in ways that only made sense if different parts of the planet were being heated and cooled on a complex schedule. The discovery of Mercury's true rotation also highlighted the importance of making careful measurements rather than relying on theoretical predictions. The assumption that Mercury should be tidally locked seemed so reasonable, so well grounded in our understanding of gravitational physics, that it took detailed observations to reveal the more subtle reality of resonant locking. Mercury's 3:2 resonance has remained stable for billions of years, and it will likely continue for billions more. The gravitational forces that created this configuration are still operating today, maintaining the delicate balance between rotation and orbit that gives Mercury its unique day-night cycle. It's a testament to the precision of celestial mechanics, where tiny differences in initial conditions can lead to dramatically different outcomes. This resonance also makes Mercury an excellent natural laboratory for studying tidal forces and their effects on planetary rotation. The same physics that shaped Mercury's rotation operate throughout the solar system, affecting the spins of planets and moons everywhere. By understanding how Mercury reached its current state, astronomers can better predict how other worlds might evolve under similar conditions. There's something almost musical about Mercury's 3:2 resonance, a cosmic rhythm where rotation and orbit harmonize in a ratio of simple integers. It's reminiscent of the mathematical relationships that create harmony in music, where frequencies that relate to each other in simple ratios produce pleasing chords. Mercury's motion creates a kind of gravitational music, a celestial symphony played out in the language of orbital mechanics. For future visitors to Mercury, the planet's strange day-night cycle would present unique challenges and opportunities. Mission planners would need to account for the 176-day solar day when designing solar panels, thermal management systems, and operational schedules. But they would also have the opportunity to witness some of the most spectacular solar phenomena in the solar system: the double sunrise, the changing size of the sun, and the extreme temperature variations that make Mercury such a world of contrasts. The 3:2 resonance reminds us that the universe is full of unexpected harmonies and hidden relationships. What initially appeared to be a simple case of tidal locking turned out to be something far more subtle and beautiful, a gravitational dance between Mercury and the Sun that has been playing out for billions of years. In Mercury's strange day-night cycle, we see yet another example of how this small planet continues to surprise us, challenging our assumptions and revealing new wonders in the cosmic clockwork that governs our solar system. As Mercury continues its swift journey around the Sun, rotating 3 times for every 2 orbits with mathematical precision, it carries with it this ancient rhythm, this celestial timekeeper that marks the passage of days and years in ways that only a world so close to our star could experience. In its strange dance with time itself, Mercury shows us that even the most fundamental concepts, like the length of a day, can be far stranger and more wonderful than our earthbound experience might suggest. There's something wonderfully poetic about the idea of sending messengers to visit the messenger planet. For thousands of years, Mercury has been playing cosmic postal service, carrying its cryptic messages between the dawn and evening skies, appearing briefly to those patient enough to look, then vanishing again into the sun's overwhelming light. When humanity finally developed the ability to send our own emissaries across the solar system, the irony wasn't lost on mission planners. We were going to deliver a message to the very planet that had been delivering messages to us since the beginning of recorded history. But visiting Mercury, as it turns out, is rather like trying to approach a celebrity who's always surrounded by bodyguards. In Mercury's case, the bodyguard is the Sun itself, a brilliant, overwhelming presence that makes getting close to Mercury extraordinarily difficult. You can't simply point a spacecraft at Mercury and fire the engines. The gravitational pull of the Sun is so strong in the inner solar system that any direct approach would likely send your carefully crafted explorer tumbling into our star like a moth drawn to a flame. Picture the challenge facing engineers in the early 1970s as they planned humanity's first visit to Mercury. They had to design a spacecraft that could survive radiation levels 10 times higher than anything in Earth orbit, temperature swings that would make Mercury's own surface extremes seem mild, and a journey through gravitational forces so complex that the slightest miscalculation could doom the mission. It was like planning to visit a friend who lived inside a furnace, while navigating through a maze of invisible currents that could sweep you away if you took one wrong step. The solution they devised was so elegant it almost seemed like cheating. Instead of fighting the sun's gravity, they decided to use the planets themselves as stepping stones. Mariner 10, launched in November 1973, would first visit Venus, borrowing some of that planet's orbital energy to redirect itself toward Mercury. It was humanity's first deliberate use of what space engineers call a gravity assist, essentially asking Venus to give the spacecraft a friendly push in the right direction. Imagine Mariner 10's journey as a cosmic game of billiards, where the spacecraft had to bank shot off Venus to reach Mercury. The timing had to be perfect, the angles precisely calculated, and the spacecraft's trajectory planned down to the meter. There were no second chances. If the Venus flyby didn't work exactly as planned, Mariner 10 would either miss Mercury entirely or find itself on a collision course with the Sun. The flyby worked beautifully, sending Mariner 10 diving into the inner solar system on a trajectory that would carry it past Mercury not once, but 3 times over the course of a year. But the gravity assist came with an unexpected limitation. The orbital path it created meant that Mariner 10 would always approach Mercury from the same angle, seeing only the same hemisphere during each encounter. It was like meeting someone fascinating at a party, but they always stood in the same position, so you could only ever see half their face. When the first images from Mercury began arriving at Earth in March 1974, they revealed a world that was both familiar and utterly alien. The cratered landscape looked remarkably similar to our moon, but there were subtle differences: the way shadows fell across the terrain, the distribution of large and small craters, the evidence of geological processes that had no equivalent on our lunar companion. Engineers and scientists crowded around computer screens, watching as each new image painted in another small piece of Mercury's portrait. The spacecraft was revealing Mercury's personality through these carefully transmitted photographs. Here was a world that had endured incredible violence, impacts that would have shattered smaller bodies, yet had somehow maintained its essential character. The images showed ancient scars and more recent features, evidence of a complex geological history that was only beginning to be understood. Mariner 10 also discovered something completely unexpected. Mercury had a magnetic field. For such a small planet, this was almost unthinkable. Magnetic fields are typically generated by the churning of molten metal in a planet's core, and most scientists assumed that Mercury was too small to maintain the kind of internal heat necessary to keep its core molten. Yet there it was, weak compared to Earth's magnetic field, but definitely present, creating a miniature magnetosphere around the planet. The discovery raised immediate questions that wouldn't be answered for decades. How could such a small world generate its own magnetic field? What did this tell us about Mercury's internal structure? Was there still geological activity happening inside this apparently dead planet? Mariner 10 had answered some questions about Mercury, but in the way of all good scientific missions, it had raised even more. After Mariner 10's 3 encounters with Mercury, the little spacecraft continued on its own orbit around the Sun, eventually running out of fuel and falling silent. Mercury returned to its ancient solitude, carrying the new knowledge that at least one species in the solar system had developed the technology to send mechanical ambassadors across interplanetary space. The messenger planet had been visited by messengers from Earth. But for more than 30 years after Mariner 10's final flyby, Mercury remained largely unexplored. Other planets received multiple visitors. Mars became a second home for rovers and landers. Jupiter and Saturn were explored by several missions, and even distant Pluto eventually had its portrait taken by New Horizons. Mercury, despite being our closest planetary neighbour after Venus, remained mysterious, known only from those tantalising glimpses provided by Mariner 10's partial reconnaissance. The challenge wasn't lack of interest. Mercury had plenty of unanswered questions waiting for investigation. The problem was the sheer technical difficulty of getting there, and, even more challenging, staying there. Any spacecraft that wanted to orbit Mercury, rather than simply flying past, would need to lose enormous amounts of energy to avoid falling into the Sun. The fuel requirements were staggering, and the engineering challenges seemed almost insurmountable. In 2004, NASA finally launched a mission ambitious enough to tackle these challenges. Messenger, a name that perfectly captured both the scientific goals and the poetic appropriateness of the mission, began a journey that would make Mariner 10's complex trajectory look simple by comparison. To reach Mercury orbit, Messenger would need to fly past Earth once, Venus twice, and Mercury itself 3 times, using each encounter to gradually shed energy and spiral slowly into the inner solar system. The spacecraft's 7-year journey to Mercury was like watching a cosmic ballet performed in slow motion. Each planetary flyby had to be timed perfectly, executed with precision measured in meters and seconds, building momentum toward the final goal of Mercury orbit. Mission planners spent years calculating and recalculating trajectories, accounting for every gravitational influence, every tiny course correction, every minute detail that could affect the spacecraft's path. When Messenger finally entered orbit around Mercury in March 2011, it marked the beginning of an extraordinary chapter in planetary exploration. For the first time, humanity had a permanent electronic ambassador in residence around the messenger planet. Day after day, orbit after orbit, Messenger began mapping Mercury's surface in unprecedented detail, measuring its magnetic field, analyzing its thin atmosphere, and slowly revealing the full face of a world that had kept half of itself hidden for nearly 40 years. The images that flowed back to Earth showed a Mercury far more complex and interesting than anyone had imagined. The spacecraft revealed ancient volcanic plains, mysterious hollows that seem to be actively forming even today, and evidence of past geological activity that suggested Mercury had once been a much more dynamic world. Each new discovery added another layer to Mercury's story, like slowly peeling back the pages of an ancient manuscript written in stone and metal. Perhaps most remarkably, Messenger confirmed the existence of water ice in Mercury's polar regions, those permanently shadowed craters where ancient comets had delivered their frozen cargo and where it remained preserved in the coldest refrigerators in the inner solar system. The discovery transformed Mercury from a simple, sun-baked rock into a world of hidden complexity and unexpected treasures. For 4 years, Messenger continued its patient survey of Mercury, slowly losing altitude as the planet's gravity pulled it closer to the surface. The mission was extended multiple times as scientists realized how much there was still to learn, but eventually the spacecraft's fuel reserves were exhausted. In April 2015, Messenger made its final contribution to Mercury science by deliberately crashing into the planet's surface, creating a new crater that would become part of Mercury's geological record. Today, Mercury has a new visitor. Bepi Colombo, a joint mission between the European Space Agency and the Japan Aerospace Exploration Agency, arrived at Mercury in 2021 after its own complex journey through the inner solar system. This mission represents an even more ambitious approach to Mercury exploration, with multiple spacecraft working together to study different aspects of the planet's environment. Bepi Colombo's journey to Mercury involved its own series of planetary flybys and gravitational assists, a carefully choreographed dance through the solar system that took 7 years to complete. The mission includes not one but 2 orbiters that will study Mercury from different perspectives, like having multiple observers examining a complex work of art from various angles to understand its full meaning. As these mechanical messengers continue their work around Mercury, they're gradually building a complete picture of our most enigmatic planetary neighbour. Each orbit reveals new details, each measurement adds to our understanding, each discovery opens new questions about how small worlds form and evolve in the intense environment of the inner solar system. There's something deeply satisfying about the fact that Mercury, the ancient messenger of the gods, has become the recipient of some of humanity's most sophisticated technological messages. Our spacecraft carry with them the accumulated knowledge and curiosity of our entire species, encoded in their instruments and computers, transmitted across millions of kilometers of space to gradually decode the secrets that Mercury has been keeping for billions of years. In sending these mechanical explorers to Mercury, we've completed a circle that began when our ancestors first noticed that bright point of light, dancing between dawn and dusk. We've gone from receiving Mercury's messages to sending our own, from wondering about its nature to slowly understanding its history, from seeing it as a mysterious wanderer to recognizing it as a complex world with its own unique story to tell. And perhaps that's the most beautiful aspect of our robotic exploration of Mercury. It represents not conquest or mastery, but conversation. We're finally talking back to the messenger planet, asking our own questions, sharing our own observations, participating in a dialogue between worlds that spans the vast distances of space and the even vaster spans of time that separate the birth of planets from the emergence of beings curious enough to wonder about their origins. Have you ever wondered what it would be like to meet the oldest member of your family? Not just someone who's lived a long time, but someone who remembers events from before you were born, before your parents were born, before anyone you know existed. Someone whose very presence carries the weight of ancient stories, whose weathered hands have touched history itself. Mercury is a bit like that ancient relative, carrying memories in its iron bones that stretch back to the very beginning of our solar system's story. It has witnessed events so old and fundamental that they shaped not just Mercury itself, but the entire cosmic neighborhood we call home. When you really think about it, Mercury is like a living fossil of planetary formation. Not fossils in the sense of ancient life, but a fossil of the processes that create worlds. Every aspect of its existence, from its oversized iron core to its battered, crater-covered surface, tells a story about conditions that existed when the solar system was young and chaotic. It's as if Mercury has been carefully preserved in cosmic amber, maintaining its essential character across billions of years, while other worlds have been transformed beyond recognition. Picture the solar system as it was over 4.5 billion years ago, not the orderly arrangement of planets we know today, but a chaotic construction site where worlds were still being built from cosmic dust and debris. If you could somehow travel back to witness that ancient time, you would see a solar system that looked more like a cosmic blizzard than the serene arrangement of planets we're familiar with. Chunks of rock and metal careened through space at tremendous speeds, colliding and merging in an endless symphony of creation and destruction. The night sky would have been brilliant with the glow of impacts, the light of forming worlds being born in fire and violence. The sun was younger then, burning with a different intensity, surrounded by a vast disk of material that swirled and collided in an endless dance of accretion. This protoplanetary disk stretched far beyond where Pluto orbits today, a spinning carousel of dust and gas that gradually organized itself into the planets we know. But close to the Sun, where Mercury was taking shape, conditions were so extreme they would have been unimaginable to any observer, fortunate enough to witness them from a safe distance. Close to the young Sun, where Mercury was forming, the heat was so intense that most materials simply couldn't exist in solid form. Water would have been vapor, complex organic molecules would have been torn apart, and even many types of rock would have been reduced to gas. It was like trying to build a sandcastle inside a furnace. Only the most heat-resistant materials could survive long enough to stick together and grow into something larger. This cosmic forge created Mercury as we know it today, a world made primarily of the toughest, most stubborn materials in the solar system. Iron and nickel, those dependable metals that can withstand almost any temperature, became the dominant ingredients in Mercury's recipe. It's as if the universe was sorting materials by their ability to endure extreme conditions, and Mercury became the repository for everything that refused to give up in the face of stellar fire. You can almost imagine Mercury's formation as a cosmic survival test, where only the most resilient materials earned a place in the growing planet. Silicate rocks that would have been perfectly at home in Earth's crust were vaporized before they could contribute to Mercury's construction. Volatile compounds that make up the atmospheres of the outer planets were swept away like smoke in a hurricane. What remained to build Mercury were the cosmic equivalents of titanium and steel, materials so tough they could withstand conditions that would destroy almost anything else. The result is a planet that feels almost intentionally engineered for endurance. Mercury's enormous iron core, making up about 75% of the planet's radius, is like a cosmic anchor that has kept the planet stable through billions of years of gravitational chaos, while other worlds in the inner solar system have been reshaped by tectonics, volcanism, and atmospheric evolution. Mercury has maintained its essential character with remarkable consistency. But Mercury's story might be even more dramatic than this already extraordinary origin suggests. Some scientists wonder whether Mercury started out as a larger, more typical rocky planet, only to have most of its outer layers stripped away by a collision so violent it defies easy imagination. In this scenario, what we see today as Mercury is actually the exposed heart of what was once a much larger world, a planetary core laid bare by cosmic catastrophe. Imagine such an impact. Another world, perhaps the size of Mars, careening through the early solar system on a collision course with the young Mercury. The impact would have been like nothing we can easily comprehend, energetic enough to vaporize continents, to blast away entire layers of planetary crust, to turn solid rock into glowing plasma that spread across millions of kilometers of space. When the violence finally ended and the debris settled, what remained was Mercury as we know it, small, dense, and metal-rich, like a cosmic fossil of that ancient catastrophe. Whether Mercury's unusual composition comes from its formation in extreme conditions or from later catastrophic modification, it serves as a kind of planetary time capsule. In studying Mercury, we're looking directly at materials and processes that date back to the solar system's youth. It's like having access to baby pictures of planets, showing us what worlds looked like when they were still figuring out how to be planets. Mercury's geological stillness makes it an almost perfect preservationist, like a cosmic librarian who's been carefully maintaining the same collection for billions of years. Unlike Earth, where constant change erases and overwrites the historical record through weathering, tectonics, and biological processes, Mercury has maintained its ancient features with remarkable fidelity. Walking across Mercury's surface today, if such a thing were possible, would be like walking through a museum where the exhibits have remained unchanged for eons. The craters on its surface aren't just scars from random impacts. They're a carefully preserved archive of what the early solar system was like, when debris was still flying around like cosmic shrapnel. Each crater is a time capsule, preserving not just the moment of impact, but also information about the object that created it. The size of the crater tells us about the size of the impactor. The shape and structure reveal details about the angle and speed of collision. The distribution of debris around the rim speaks to the energy and violence of the event. But perhaps most remarkably, Mercury's craters preserve information about timing, which impacts happened early in solar system history, and which occurred more recently. By studying the way smaller craters overlay larger ones, scientists can read Mercury's surface like geological layers in Earth's crust, each telling a story about a different chapter in cosmic history. It's crater archaeology, where the goal isn't to uncover ancient civilizations, but to reconstruct the violent youth of our planetary neighborhood. This preservation of ancient features makes Mercury invaluable for understanding not just our own solar system's history, but planetary evolution in general. As astronomers discover planets around other stars, they find many worlds that orbit much closer to their host stars than Mercury does to our Sun. These distant planets probably experience conditions even more extreme than Mercury's, and understanding how Mercury has responded to its challenging environment helps us predict what might happen to those far-off worlds. Mercury's magnetic field offers another glimpse into the deep processes that shape planets. The fact that such a small world can generate and maintain its own magnetic field suggests that planetary interiors are more dynamic and long-lived than anyone expected. Mercury's magnetic field isn't just a curiosity. It's evidence that even small worlds can harbour complex internal processes that persist for billions of years. This discovery has implications that reach far beyond our solar system. Among the thousands of exoplanets that have been discovered, many are smaller than Earth and orbit much closer to their stars than Mercury does to the Sun. If Mercury can maintain a magnetic field despite its small size and extreme conditions, perhaps these distant worlds can too. And if they have magnetic fields, they might be able to protect their atmospheres from being stripped away by stellar radiation, potentially making them more hospitable than we might otherwise expect. Mercury's role as a natural laboratory extends to its unusual rotation as well. The gravitational forces that locked Mercury into its strange 3-to-2 spin-orbit resonance, 3 rotations for every 2 orbits around the Sun, operate throughout the universe. By understanding how Mercury reached this configuration, astronomers can better predict the rotational evolution of planets everywhere, particularly those that orbit very close to their stars. The recent discovery of water ice in Mercury's polar regions has added yet another dimension to its importance for understanding planetary evolution. The fact that water can survive on the hottest planet in the solar system, hidden in permanently shadowed craters, suggests that even worlds in extremely hostile environments might retain pockets of more moderate conditions. This discovery expands our thinking about habitability and the distribution of water throughout the galaxy. Perhaps most importantly, Mercury serves as a reminder that planetary formation is not a gentle, predictable process, but a chaotic and often violent series of events that can create worlds far stranger than our Earth-based experience might suggest. Mercury's metal-rich composition, its unusual magnetic field, its extreme temperature variations, and its hidden ice deposits all speak to the creative power of cosmic forces operating under extreme conditions. In many ways, Mercury embodies the principle that extremes often reveal fundamental truths. Just as scientists sometimes study materials under extreme pressures and temperatures to understand their basic properties, Mercury's extreme environment has stripped away the complexities that make other planets harder to understand, revealing planetary physics in its most essential form. The story Mercury tells about solar system evolution is ultimately a story about survival and adaptation. It's a world that has endured conditions that would destroy most planets, yet it has not only survived but maintained its essential character for over 4 billion years. Mercury shows us that rocky planets are far more resilient than we might expect, capable of weathering catastrophic impacts, extreme temperature variations, and the relentless bombardment of solar radiation, while still preserving records of their ancient past. As we continue to discover planets around other stars, Mercury provides a crucial reference point for understanding what small, close-in rocky planets might be like. It suggests that such worlds, far from being boring or uniform, might harbour their own unique characteristics and surprising features. Mercury reminds us that even in the most challenging environments, planets can develop their own distinct personalities and tell their own remarkable stories. There's something deeply satisfying about the idea that Mercury, the swiftest planet and the most elusive to observe, should also be one of our most important teachers about planetary evolution. It's as if the universe has a sense of poetic justice. The planet that spent millennia playing hide-and-seek with human observers turns out to hold some of the most important clues about how planetary systems work. In its swift orbit around the Sun, Mercury carries with it the memories of cosmic violence and creation, the evidence of processes that shaped not just our solar system, but perhaps planetary systems throughout the galaxy. Every feature of Mercury, From its oversized core to its thin atmosphere, from its extreme temperature variations to its hidden polar ice, represents a piece of the puzzle that scientists are still working to complete. Mercury's story is ultimately one of endurance and adaptation, but also of revelation. It shows us that rocky planets are far more resilient than we might expect, capable of weathering catastrophic impacts, extreme temperature variations, and the relentless bombardment of solar radiation, while still preserving records of their ancient past. But more than that, Mercury reveals that even worlds formed under the most extreme conditions can develop their own unique characteristics and surprising features. Consider how many assumptions Mercury has challenged over the years. Scientists assumed it was tidally locked until careful observations revealed its strange 3-2 resonance. They assumed such a small planet couldn't maintain a magnetic field until spacecraft measurements proved otherwise. They assumed its sun-baked surface couldn't possibly harbour water ice until radar observations detected it hiding in polar shadows. Each discovery has forced us to expand our thinking about what's possible for planets, especially small ones orbiting close to their stars. This pattern of surprise and discovery suggests that Mercury still has secrets to reveal. Despite decades of study and multiple spacecraft missions, we're probably still only scratching the surface of understanding this remarkable world. Future missions may uncover evidence of past volcanic activity, discover new types of geological features, or reveal unexpected connections between Mercury's interior dynamics and its surface evolution. As we continue to discover planets around other stars, Mercury provides a crucial reference point for understanding what small, close-in rocky planets might be like throughout the galaxy. The thousands of exoplanets discovered so far include many that orbit even closer to their stars than Mercury does to the Sun. Understanding how Mercury has survived and evolved in such challenging conditions helps us predict what these distant worlds might be experiencing and what features they might have developed. Mercury stands as a testament to the fact that even the smallest worlds can play outsized roles in the cosmic story. In its metal heart and battered surface, in its hidden ice and unexpected magnetic field, in its strange rotation and extreme environment, Mercury holds clues to some of the biggest questions in planetary science. How do worlds form under extreme conditions? How do they survive billions of years of cosmic bombardment? What makes a planet capable of retaining its essential character across geological ages? The answers Mercury provides reach far beyond our own solar system. They help us understand planetary formation around other stars, predict the evolution of close-in exoplanets, and appreciate the complex processes that can create habitable environments even under seemingly impossible conditions. Mercury reminds us that the universe is creative in ways we're still learning to appreciate, capable of producing worlds that challenge our expectations and expand our understanding of what's possible. As Mercury continues its endless, swift dance around the Sun, it carries these ancient secrets with quiet dignity, a small world that has seen everything and remembers it all, waiting patiently for us to learn how to read the stories written in its rocks and craters and magnetic field. In understanding Mercury, we understand something fundamental about the processes that create and shape worlds, not just in our solar system, but throughout the universe where countless other planets are following their own paths through the cosmic forge of stellar fire and gravitational forces. As our gentle journey through Mercury's story draws to a close, perhaps you find yourself looking at this small planet with entirely different eyes than when we began. What started as that elusive point of light playing hide-and-seek in the twilight sky has revealed itself to be one of the most fascinating and complex worlds in our solar system. Mercury, the swift messenger who has been carrying cosmic secrets for over 4 billion years, has finally begun to share some of those secrets with us. There's something wonderfully fitting about ending our exploration of Mercury as night deepens around you. Mercury itself knows intimately the rhythm of light and shadow, day and night, though on a scale that dwarfs our earthly experience. While you might experience the gentle transition from evening to night over the course of a few hours, Mercury experiences a single day that stretches across 176 Earth days, a languid, cosmic breathing that makes our planetary rhythms seem almost frantic by comparison. Throughout our journey together, we've discovered a world that consistently defies expectations. Mercury has taught us that planets don't always follow the rules we think they should. Who would have expected to find water ice on the hottest planet in the solar system? Who could have predicted that such a small world would maintain its own magnetic field, or that its rotation would be locked in such an elegant 3-2 dance with its orbit around the Sun? These discoveries remind us that the universe delights in paradox and surprise. Mercury embodies this cosmic sense of humour, a planet that manages to be both the closest to the Sun and home to some of the coldest places in the solar system, both the swiftest in its orbit and the most patient in its day-night cycle, both the smallest of the planets and one of the most important for understanding how worlds form and evolve. In many ways, Mercury serves as a bridge between the familiar and the alien. Its size is comparable to our Moon, making it somehow more approachable than the gas giants with their bewildering scales and exotic chemistries. Yet its environment is so extreme that it pushes the boundaries of what we consider possible for a rocky world. Standing on Mercury would be like visiting a familiar neighbour, who turns out to live in circumstances so unusual that you have to completely reconsider what you thought you knew about them. The story of our exploration of Mercury is also a story about human persistence and ingenuity. For thousands of years, Mercury remained largely mysterious, visible only as brief appearances in dawn and dusk skies. Ancient astronomers thought they were seeing two different objects, the morning star and the evening star, until careful observation revealed the truth of Mercury's singular identity. Even then, Mercury kept most of its secrets hidden, too close to the Sun for easy telescopic study. It took the space age to truly meet Mercury face to face, and even then the engineering challenges were extraordinary. The spacecraft we've sent to Mercury had to navigate gravitational mazes, survive radiation levels that would destroy most electronic equipment, and operate in temperature extremes that swing from hot enough to melt lead to cold enough to freeze air solid. The fact that we've managed to orbit Mercury, map its surface, and measure its composition represents one of the great triumphs of human exploration. Yet for all our technological achievements, there's something humbling about Mercury's ancient presence in our skies. This small world has been faithfully keeping its swift orbit around the Sun since long before the first life stirred in Earth's oceans. It has witnessed the entire history of our planet, from its molten youth to the emergence of continents, oceans, and eventually the curious species that would one day build telescopes and spacecraft to study distant worlds. Mercury has been a constant companion throughout the story of life on Earth, though we've only recently developed the ability to appreciate its companionship. Every sunrise and sunset you've ever witnessed has occurred while Mercury was somewhere in its eternal dance around the Sun, sometimes racing ahead of our star as the morning herald, sometimes following behind as the evening sentinel, always maintaining the precise rhythm that gravity and celestial mechanics demand. The ice hidden in Mercury's polar craters adds another layer of poetry to its story. Here's a planet that lives so close to stellar fire that most of its surface could melt metal, yet it manages to preserve water from ancient comets in the deepest shadows of its coldest craters. It's as if Mercury is keeping a small piece of the outer solar system's ice and chemistry safe in the inner solar system's furnace, a cosmic safety deposit box maintaining samples of materials that might otherwise be destroyed by the sun's intense radiation. This hidden ice also connects Mercury to the broader story of water in the solar system and the potential for life beyond Earth. The same comets that delivered water to Mercury's polar refuges probably also contributed to Earth's oceans. In Mercury's frozen deposits, we see evidence of the cosmic processes that distributed water throughout the solar system, creating the conditions that would eventually allow life to flourish on at least one world we know of. Mercury's role as a natural laboratory for extreme physics continues to yield insights that extend far beyond our own solar system. As astronomers discover more and more exoplanets, particularly the small, rocky worlds that orbit very close to their host stars, Mercury provides our best example of how planets behave under such challenging conditions. The lessons we learn from Mercury's magnetic field, its thermal evolution, its atmospheric dynamics and its geological processes help us understand what might be happening on distant worlds we may never visit directly. There's also something profoundly satisfying about the fact that Mercury, despite being the most challenging planet to study, has revealed some of the most important insights about planetary formation and evolution. It reminds us that the most difficult questions often yield the most valuable answers, and that persistence in the face of technical challenges can lead to discoveries that reshape our understanding of the cosmos. As you settle into the quiet of this evening, perhaps you'll remember that Mercury is out there somewhere, following its ancient path around the sun. It might be hidden in the sun's glare, invisible to our eyes, but faithfully maintaining its swift orbit. Or it might be making one of its rare appearances in the twilight sky, offering patient observers a chance to glimpse this most elusive of worlds. Whether visible or hidden, Mercury continues its role as guardian of the inner realm, the small world that has claimed the territory closest to our star and learned to thrive in conditions that would be impossible for most other worlds. In its endurance, we see a reminder that life and worlds can adapt to almost any environment, finding ways to survive and even prosper under the most challenging circumstances. Mercury's story is ultimately a story about resilience, adaptation, and the endless creativity of cosmic processes. It shows us that even under extreme conditions, worlds can develop their own unique characteristics, maintain their essential nature across billions of years, and harbour surprises that challenge our understanding of what's possible. In the gentle silence of this night, as you perhaps drift toward your own rest, Mercury continues its eternal vigil in the inner solar system. It carries with it the memories of cosmic violence and creation, the evidence of how worlds form and survive, and the quiet lessons of a planet that has learned to dance with stellar fire while maintaining its own cool secrets in the shadows. Mercury, swift messenger of the dawn, keeper of ancient ice, guardian of the inner realm, may its story inspire you to look up at the twilight sky with new appreciation for the cosmic ballet playing out above us, and to remember that even the smallest and most distant worlds can teach us profound truths about the universe we call home. Sweet dreams, fellow travellers of the cosmos. Mercury keeps watch over the inner solar system, as it has for billions of years, ready to share more of its secrets with those patient and curious enough to seek them out. Clear skies and gentle starlight, the sleepy astronomer